All right, here we go. Question for you. When this laser hits this mirror, hypothesize where it's going to reflect, like point, where you think it's going to end up. Ready? You're right. You're close to. See it by the light? Okay. That is because the law of reflection's pretty straightforward and very intuitive. Okay. So the law of reflection says the angle in is equal to the angle out. The angle of incidence is equal to angle of reflection. Okay. Good with that? Angle of incidence is equal to angle of reflection. Okay. Okay. Now, here's a important detail. When we're measuring the angle with light, we're always going to be measuring it from the normal line. Remember, normal force is perpendicular to the surface. Normal line is also perpendicular to the surface. We're going to measure this angle, not that angle. Okay? And that's going to be true throughout the rest of this chapter, which, by the way, we'll have a test the last Friday of class before finals. Oh. Better than the Monday of finals, which it was going to be. So I had to truncate it a little bit. Going for 3 tests per quarter. Otherwise, it's like if you like bombed one, you have no hope of recovery. Okay. So, question. In order for you to see something, light has to reflect off of the object and go into your eyes. Can you see that laser dot?
Yeah.
Yes. You know what? I can too. And so can everybody else except for Adam, because the light's going off of that object into your eye, into my eye, into everybody else's eye. You okay? How is that obeying the law of reflection? Because it's going into everybody's eye. It's a law, right? I mean, it's called a law if it doesn't work all the time. You see the conundrum? Okay. So, it's not violating anything, just the surface it's bouncing off of is rough. And so when the laser comes in, it's bouncing off at different angles depending on where it hits. You okay with that? Okay. So we're able to say, yep, it is still obeying the law of reflection, and it's going off in all directions because this is rough. So the follow-up question to that would be, so what would happen if the surface wasn't rough? it was like infinitely smooth. So watch what happens to the brightness. Sorry, video people. Watch what happens to the brightness of the laser when it goes from the whiteboard to the mirror. Yes, I know it reflects off, but what happens to the brightness of the laser beam on the mirror? Sorry, going from whiteboard to mirror. It gets less. Why? It gets dimmer. Why? Because most of it's being reflected off onto the ceiling. But is it infinitely smooth? How do you know? You can still see it. There's some still diffused reflection going on. Good with that? The smoother that mirror, the less of that laser you can see, unless you're standing right where it's hitting you there. Good with that? And no, we don't have an infinitely smooth mirror. Yep. All right. So, as you looking at plane mirrors, so these are just flat mirrors. Your eyeball is the catcher, the receiver of light. So light's coming off of the object, obeying the law of reflection, and going into your eye. Right? So your angle of incidence, let's try that a little bit. Obeys the law of reflection. So angle of incidence equals the angle of reflection. Okay? We think we see the object right here. So this would be your object distance. And this would be your image distance. In a plane mirror, your object distance equals your image distance. We see that demonstrated all the time. Anytime you look in a mirror. But it's humorous when you stick a mirror in front of a baby or a puppy and they think they see another baby or puppy, and the baby's like, ooh, and they're like, oh, I want to go touch. And like as it gets closer, so does the other baby get closer, and like the puppy's like, as it gets aggressive, the other thing gets like it's head bite, yeah, whatever. Get to that? Okay. Object distance equals image distance. Good? Okay. So, question, demonstration. I showed mirror. Sorry, this is not public knowledge. All right. So, are you seeing classmates? Can you see faces? Yes? Okay. Ethan, can you see yourself?
No.
No. Can you see Franny?
Yeah.
Franny, can you see yourself?
No.
Can you see Ethan?
Yeah.
So, if you can see someone in a mirror, they can see you. It's creepy. Okay? Do you see the path that the light's going? Coming off of Ethan, bouncing off into Franny's eyes, coming off of Franny into Ethan's eyes. Does that make sense? Okay. Some truckers have on their cab a sign that says, "Make sure you can see me in the mirror." Because if you can see them in the mirror, they can see you, and you're not in their blind spot. That make sense? Okay. In a mirror, in a plane mirror, the right and left are inverted. In the front of an ambulance, they write "Snabli-blma." Why would they write that just jarbled, like gibber jarblelous? Oh, I bet you they can see it. So, why would they write it backwards? Front of an ambulance. Where are you going to see the front of an ambulance? As it comes from behind you. In your rear view mirror. So pretend like you're driving that way. Pretend like the mirror that you have is your rear view mirror. Look at boom, look at that. Whoa. There we go, that. Right, left, inverted. Okay? Another question for you. What length of a mirror do you need to capture your entire body? Like you want to make sure your whole outfit is like boom, like look at me, I'm ready for school today. What length mirror do you need? All right. Everybody have a guess? See the question on the board. Need 2 volunteers. 1, 2. Perfect. All right. Holly, you want to hold the mirror or look in the mirror? All right, Parker. So you just hold it up. Try to keep it vertical. Parker, can you see the top of your head?
It's my eyes.
Okay, raise it up a little bit. Can you see the top of your head? Okay, roll it. Move it down until just about the, okay. So there's that. Now I'm going to start covering up the bottom. You tell me when your toes are about to disappear.
Right.
All right, you good with that?
Mm-hmm.
Okay, now move closer. Can you still see your toes?
Yeah.
Can you still see your head?
Yeah.
Okay, move back. Like keep going, keep going, keep going, keep going. Take a couple. Oops, sorry. Can you still see your whole body?
Yeah.
Perfect. All right. Thank you much. Good job. What did you get? Oh. So that was about half his height. That was kind of a. All right, so there to about there. About half his height. Yeah? Okay. Takes half your body length. See the entire. So.
No, it's still.
Here's your mirror. You have your full length body mirror. But you only need light coming from the top of your head, bounces to your eye, you only need that part. And light coming off of your toes, going into your eyes. You only need this part of the mirror to see your entire body. Regardless of how close you are. Or out here, does not matter. Good with that? You still doubt me. Get it? So what I want you to do is I want to take your mirror, I want you to look at yourself, wink, so close one eye, and look to see what portion of your face is captured in this mirror. From like ear to ear, from chin to eyebrow. You got a reference point? Okay, pull it close. Hold it at arm's length. Did the amount of your face change? The amount of your face did not change. Okay? Because when you are looking at yourself, it doesn't matter. Like, you're going to have the same percentage of your body in the mirror at any distance. It looks like it's further away. Like, you get like the image distance matches the object distance, but you keep the same amount. Now, this does not apply when you're looking at other things. Okay? So when I'm doing this, I can see half the classroom over here when it's close. But when it's right here, all I got is Sam. That makes sense? Okay? All right. Two-way mirrors. This is the thing where like one side looks like a window, the other side looks like a mirror. That's because the two-way mirrors, they're actually just semi-reflective. Some of the light gets through, some of it's reflected off. The side that looks like a mirror is the brighter of the two sides. So in an interrogation room, they're going to make the bright, like the questioning bright, and the people who are spying dark. If they would turn on the lights in the spying room and turned off the lights in the interrogation room, it would flip-flop. Okay? Think about it in terms of just how a normal window works. In the daytime, when you're trying to look inside, it's bright outside. You have to like cover up to be able to see through the reflection to see inside. But at night, when the inside is bright, it's super easy to see through the window into the house. Good with that? Yep. Or flip-flop it if you're on the inside trying to look out. All right, spherical mirrors, not plain mirrors, but mirrors that are curved. Okay, so you got concave, and convex. Concave, these are the ones that look like a bowl going into a cave. If you bring parallel rays of light, they'll bring to a focal point, a focus point. You might have made like Girl Scouts and Boy Scouts, like a little solar oven, cooked hot dogs or marshmallows right here, really inefficiently, took forever, but it could. Okay, it's kind of like how radar works, capturing radio waves at that point there, at the focal point. Good with that? Okay. So concave. Okay. Look at the concave part. Hold it at arm's length. Okay. How would you describe your image? Are you right side up or upside down?
Upside down.
Upside down. We're going to call that inverted. Good with that? Is your image smaller or larger than you? Smaller. We're going to call that characteristic shrunken. The image is shrunken compared to the object. Okay? Now, the focal length for these is like pretty close. We're looking at an object far away from the focal point, beyond the focal point. But if we bring the object and we bring it closer than the focal point, so bring it like it's like touching my nose. Look at your eyeball. Okay. Is the image upright or inverted? Does your eyeball look upright or is it upside down?
Right. Sure.
Upright. And is it shrunken or enlarged? It's enlarged. Oh, yeah. There it is. Look at that. Boom. Okay. It is enlarged. This is how makeup mirrors work. But their focal length is a lot longer. Like they're not as curved as this one, as aggressively. You good with that?
Yeah.
Okay. Now, the other side is a convex mirror. The way I remember that, concave, you go into the mirror. Convex is like you're flexing. You get a bulge. Okay? So, when rays come in, they bounce off as if they came from a focal point. You right with that? So, flip the mirror over. That's the convex to the bubble part. That's convex. How would you describe your image? Upright or inverted? Upright. And this does not matter how far is your image shrunken or enlarged depending compared to the object?
Oh, yeah.
It is shrunken. Okay. As it gets further away, it shrinks more and more. Good with that? Now, here's something cool. Take this and bring it up to your eye. You can see through this. Okay? This is semi-transparent. So it looks like when you make it, you're going to make it dark right here in front of your eye, and you can see light outside. Good with that? All right. Pass up the concave convex first. See if you can figure out how a periscope works. Like, make a periscope with a buddy. A periscope is one of those things that are like on a submarine, periscope up. You can like see over things. You need 2 ears for that. How are you gonna make it?
Joey, look at my beard.
How far can you see?
I see it.
That's a bunch of why there's something like I see everything. I see Joey. Wait, who do I see? Oh, yeah, I see Joey. That's so small. When they go back and forth.
I'll look at mine.
Chain. I can see you.
Did we get it?
Bryce. I'm not looking for long. Where am I going?
Yeah, somebody.
You're taking his.
I've done this always.
There we go. See how I'm doing it like this? I can see up and over. You see my eyes when I'm like pointing at you? Creepy. See you, computer kids. There you are. Oh, get in there. There I am. Forever. Ah! Okay. All right. Go ahead and pass those up.
Yeah, I'm like, great job.
Last challenge for today.
Are we guaranteed to Christmas? Yes.
What I want to do is you're going to take I have a laser back here. You're going to take some mirrors and you're going to bounce them, reflect that laser beam all the way to the elevator.